welcome everyone. Thanks for coming. So it's really great to have Ruslan Salakhutdinov here today. Just a short, Russ is really needs no introduction. He's just done tons of amazing work in deep learning and machine learning more broadly. I think for me, he's one of the most interesting deep learning people in the way he bridges ideas with very interesting experiments and results. So, take it away, Russ.
Thank you. Thank you, Sean. Thank you. Thanks for invitation. It's great to be back in Boston. Just to test. Is that still functional? Okay, great. It's great to be back in Boston. It's been a while. I've never been to this building, so it's great to see amazing building that you guys have here. So today, I'm going to talk about multimodal autonomous AI agents. And as I go through the talk, if you have any questions, feel free to ask questions because I think we'll have quite a bit of time. This is the work that we've done at CMU, but I think it's very relevant to the work that's happening both in industry and in academia. Okay, so we all know about large language models, right? And we all seen examples of amazing abilities of these models to do in context learning, some zero-shot abilities, have interesting representations, they carry some world knowledge and such, right? So the question is, what's next? Where are we moving? There are a lot of different directions, but one direction is building autonomous AI systems that can actually make decisions on your behalf. So for example, a lot of productive tasks, perhaps can be automated, that are done on a computer can be automated, right? And then there's a lot of opportunities to automate sort of routine set of tasks, and also augment human capabilities. So let me give you an example. How many of you have tried setting up Amazon AWS instance? Great. How many of you found the whole process sort of intuitive and easy to do? Right? Why can't I have an agent that I can just ask it to go do it on my behalf, and it should go and just do it for me, right? Why can't I create a PowerPoint slides presenting content of my paper, right? That's something that can be done. When I was a junior professor, a PhD student, I would spend a lot of time doing it. Right now, I have students who help me to do it. In fact, my students do that. But it would be nice to have agents that can go and do it on my behalf, right? Just a few examples. And today I'm going to be focusing on web agents. So you can think of these agents that have some notion of understanding of HTML or some representation of the input, coupled together with vision representation of what's happening on the web. And that sort of gives me some form of web grounding, right? Or agents that can actually do interesting tasks on the web, as one example. Let me show you, and of course, there's a lot of work that was done in that space. I'm not listing, all the papers here, but there's a lot of interest in sort of developing agents that can do interesting things on the web. Let me give you one example, right? This is a very cherry-picked example, right? But it shows you what potentially you can do. So let's say I have a task and I say navigate to a page of a good Thai restaurant in Pittsburgh. It should have at least 200 reviews and 4.5 stars. Pick the one with the highest rating, okay? And this is what the agent is actually doing. This is GPT-4o agent, and you can see that, it sort of goes on the web, it goes on Yelp, chooses to go on Yelp. It starts typing in Thai restaurant in Pittsburgh. This whole thing is done autonomously. It has some chains of thoughts reasoning, right? It goes through the pages, it scrolls, and essentially, eventually it finds the right restaurant. It says Pussy Garden. It's actually a pretty good restaurant in Pittsburgh, and then it's done, right? Next, I can say, make a reservation in this restaurant for 2 people at the earliest date. Use my name, JY, the student who was doing this project. My phone number is this, right? So now the agent goes on Google, searches for this restaurant, finds the restaurant, goes into the dates, finds sort of the next available date. You're asking it for the confirmation. It puts the right phone number, submits, and then basically stops because you need to get a confirmation. That's done on the real web, right? So it kind of like says, in summary, the next action I will perform is stop, unable to proceed without the confirmation code and stuff like that. right? Or you can, in the multimodal setting, again, you can say, help me navigate to a shirt that has this on it. So I have to have some understanding of the visual, what that is. Turns to go to Amazon, searches for it, and actually finds a shirt that has this, right? And that's it. That's the one that it found. What's interesting about these examples, again, these are highly cherry-picked examples, so don't think we have systems that can do this today, but it kind of like shows you a few settings where, the systems have some way of understanding what's happening on the web, and have a way of solving those tasks. So my talk is going to be structured in 3 steps. I'm going to introduce something we call VisualWebArena. It's a benchmark for evaluating these agents, and I'll talk a little bit about what we're doing and where the problems are. I'll talk a little bit about the search algorithms, and this is sort of a way of doing inference-time search for these agents, show some examples of what works and what doesn't. And the last part, I'll talk a little bit about how all of the stuff that we've done in the first part of the talk can be translated to actually physical agents, agents that can actually perform tasks like long horizon robotic manipulation tasks. Okay. Okay. One of the things that was done at CMU is something that's called WebArena. It's one of the most realistic web environments at the moment. It's basically has websites from some categories, popular categories like Amazon, Reddit, and GitHub. The data contains in these sort of simulators coming from real Amazon, Reddit, and GitHub. And what's interesting about these kinds of environments is that humans are, successful in terms of completing some of these tasks is like 80%, 78%, but language models are sitting at 14%. However, these tasks are designed to just use HTML code, and turns out HTML itself is very tough to deal with, right? Part of the issues just operating on HTML is that there is like JavaScript, CSS codes, and there's like you read at the web pages, they're basically incomprehensible. And then the other thing is that the context length, like if you're trying to browse through the web and you kind of like start filling in what you've seen so far, it becomes so big that these models are not doing so well. And so what we've done is we've built what we call VisualWebArena, and we design tasks, visually grounded tasks to test the abilities of these multimodal models. And we have visual inputs, visual outputs to allow some interesting and sort of realistic environments. We basically have 3 settings. One is called one-stop shop, which mimics sort of Amazon type of experience. We have Reddit and we have OS class, and OS class sort of mimics, you can think of it as like a Craigslist, where I'm browsing through, I can make postings, I can search for information there. And that information goes into LLM or visual language models, and then these language models will take actions, okay? Let me show you some examples of what these environments are looking like, and then I'll dive a little bit into definition of how we define what they are, okay? So here's an example, right? The example is, I'm showing you this bike, and I'm telling you, find the exact bike that is listed between $300 $500 and make a posting offering $10 less than the asking price. Okay, so I have to find this bike and I have to make a posting and I have to offer price less, $10 less than whatever the asking price is, right? So what the agent has to do is it basically has to, navigate to the bike category, start like finding 300 to 500. You start searching through the bikes, and eventually you find the bike. That's the bike, and then you make a posting, right? Hey, would you sell it for whatever the price is minus $10? That's all done autonomously by the agent, right? Yes.
You learn the mouse navigation policy?
I'll come back to that. The question is, like, what is happening here? What's the input? What are the action spaces? I'll go through that. But you can think of it at the high level. This is what the agent has to do, right? I'll define exactly what the state space looks like. But you can think of this whole problem as like an MDP or POMDP type of a problem, where you have states, you have actions, your agent has to take actions. There's lots of different actions you can take to sort of accomplish this task. Yes?
Are you going to say more about the arena, or can I ask a couple questions?
Yes, absolutely.
Like, how big? So you got this, like, presumably from some type of web scrape, but to have any, like there's a lot of different options here. So like how rich is this? And
yes, I'll get back to that. In terms of the sort of the environment itself, in this case, we had on the order of 900 tasks. In terms of richness, I think that we had, it's pretty rich in terms of the variety of different images and so like, and then like different ways of solving the problem. There are multiple paths, like there's multiple ways I can actually do this.
it's more, okay, so it's not really like a huge web scrape. It's more like 900 tasks and like a depth.
Exactly. Exactly.
Script, like the depth.
Exactly. But the thing about this particular environment is that it's a simulator, right? Because, and it's important that it's a simulator because if I take an action, if I click on anything, I'll generate the next state, right? So, exactly. So yes, you don't want to bike this bike. I mean, this is something that you can do. It's harder to do in the real world. Here's another example. Buy me the cheapest color printer and send it to Emily's place, as shown in the image. And you can see the Emily's place is upside down, right? And we sort of were designing these tasks because existing models are not that good in terms of solving this, right? And this is what you have to do. You actually have to find, I mean, again, these are constrained environments, and then you basically have to go, you fill the form with the address, the correct address and everything, and then you have to, and this is what the agent has to do, right? And then you complete the order, right? So it's a highly non-trivial thing to do. Here's another example where you're kind of like crawling across different websites. You can ask the question, what's this 2022 total nominal GDP of the area that produced most sugarcane in a year? And that's your starting page. What's interesting here is that you can kind of like see that Asia produced more sugarcane in 2022, but not in like 1919, right? And so you have to understand the graphics here to be able to answer that question. And so what the agent has to do is it kind of like has to, I mean, it's a human doing it, but you kind of like have to identify that it's the Brazil, you go to Wikipedia, and then you find the GDP of Brazil in 2022, right? In terms of the environment itself, how does the environment structured? Yes.
Actually, just there's a couple more seats here and there, so feel free to shuffle about if people want to explain. There's at least like 3 seats up here. There's probably a few spots, so feel free to the one there.
Oh, yes, there is also some seats over here.
One there.
Oh, yes. So in terms of the environment itself, what is this environment? So you can think of this environment as an MDP or POMDP environment. You have state, you have actions, you have observations, you have transition function. Okay. So the observations, you can either view those observations as screenshots of your web pages, kind of like what you see in here. You have HTML representation on what we call a DOM-based representation, which is like the pure HTML that generated that particular screen. And then you have, sometimes people use what's called accessibility tree, which is, you can think of it as like a cleaned up representation of your HTML, okay? So that's the input that the model, you can work with that. You also have a set of actions. And it's interesting because there's a lot of work that folks were doing to design what actions you can take on the web. A lot of these actions like clicking, hovering, what's interesting is that there is an action called type. So you want to type, you have a particular element ID and you can type the text. And so you have to generate what is it that you want to type. So it's not just discrete set of actions, but some of these actions are actually, it's a fairly rich set of actions that you can take. You can go to a particular URL, you can go back, you can go forward, you can scroll up and down. And then typically when you're solving the problem, the policy that you're building on the LLM has to generate a stop action and it has to generate the answer, right? Once it generates stop and the answer, that's the answer that you're basically either getting or you're ending up on a particular state and particular web page that basically shows you that you've solved the task. You have deterministic transition function right now. So what that means is that if I'm in a particular state and I take a particular action, there is only one state deterministic transition to the next state. So we are not operating in stochastic systems where, sometimes the web pages can change or it can dynamically change. We're thinking about extending that, but for now we have deterministic transitions. This is simulator. And we also have a reward function. Reward function right now is very simple. It's essentially 0-1 reward, which says for a particular task, if you end up in a particular state, perhaps with a specific action, then we know what the correct state should be. So if I'm asking you to solve the task, there is only one state that corresponds to solving the task. If I'm in that state, the reward is 1, otherwise it's 0. Okay? We haven't really done a setting where you're partially completing the trajectory and you get sort of high reward or not, because there's multiple traces that can reach the same state, right? So it makes it an interesting kind of like problem. Just to show you the richness of what you need to do in sort of this particular example, buy me the printer, right? You basically have to start on the homepage of what we call one-stop market, right? Step 1, you have to navigate to the printer category. So you have to click on the printer category. You have to sort by descending order. You have to click on the cheapest color printer out of these 4. You have to choose which one you have to look at the prices and figure out what the prices are, right? You have to add it to the shopping cart. Then you proceed to the checkout. And then you have to fill in the form correctly based on visual input over there. And then you have to place the order. Now, we have a value evaluation, which is our reward model. It basically says if you end up in this state, right, with all the conditions satisfied correctly, then it's 1, otherwise it's 0, right? So what's interesting is that for these kinds of things, we're trying to understand where these models are and how far we can push them. You sort of see, we looked at the shopping, there is class field, which is, again, Craigslist type representation. There's a Reddit, you can answer questions and interact. And then there's multi-site, where you have to jump between different sites to solve the task. In terms of the difficulty, you can sort of think about in terms of visual difficulty and reasoning difficulty. The way that we sort of look at the, we sort of classify these things is that reasoning difficulty, we ask humans to solve the task. These were master's students at CMU who were solving the task. And the reasoning difficulty for us, it was mainly how many clicks it takes to solve the task. And then we would record the time, how long it took people to do this. And vision, kind of like we asked people, like, was that visually difficult or not? So they would kind of give us some estimate of what it is. The point I want to make here is that about 15% of these tasks, what we call easy, both in terms of vision representation, what I'm asking you to do, and how fast I can solve the task. Usually, like, easy task, like a few clicks, you can solve the task. Okay. Yes.
I was wondering, like, all of HTML in general interfaces were built with humans in mind, so it's kind of like optimizing for our visual capacity and like how we carry out tasks. But like now we're building agents that are trying to maximize it. But for agents, you can just like show a list of printers, and then you could optimize this in very different various ways. So do you think about like shifting the paradigm to maybe in the future the HTML will have also a code about for the agent to more easily parse the website rather than going through the visual steps that a human has to go through?
Yes, that's a very good question, because the first question people would ask is that 10 years from now, these agents actually working. Perhaps we're going to be building websites for the agents, not for the humans, right? And perhaps I don't even need to go to the websites. I'll just ask my agent to go like do the task for me, and then I don't have to go to Amazon.com and like click on things, right? And so how that's going to evolve, we'll have to see. At least right now, visual information turns out to be quite useful. Understanding what's visually you see in addition to understanding the text as well. But that's a very good question, because I think that if these systems, they're not working by far at this point, but as they start working, I think the evolution of the web might actually change. We'll see. It's not going to happen overnight, but it might happen longer term. Yeah. This is what our reward function looks like. Just to highlight a couple of things. Oh, there was another question. Yes, sorry.
If you have a long chain of tasks, and it gets longer and longer, and I guess it's more probable that it makes a mistake somewhere, do you encourage the agent to self-correct its trajectory, or do you want to just restart from scratch, go to the home screen, and try again?
Very good question. How do you deal with long horizon tasks? I'll talk a little bit more about in the second part of the talk. So hold your question. I'll come back to that. It's a very good question. In terms of the reward function, you can kind of like see it's not perfect, but for example, for some tasks, there is an exact match. We know what the right answer is, right? If we're searching through the web. For some other tasks, we have some visual representation. If I'm buying, add something to the cart with the man wearing in this thing in my wish list, yeah, I'm basically saying, is this a polo shirt, is this a green shirt and such. There's like proxy evaluators. They're not perfect, but a lot of times we can at least get some reasonable evaluation function that tells me like, okay, you completed the task versus you not. And these would be reward functions that basically give you 1 or 0. Now, how does the LLM or this is visual language models are operating right now? So there are many ways that people are working on how to building these models. You can think of it as, taking the text input, which is accessibility tree or HTML representation. It's very cluttered. And then in addition to that representation, you also have visual representation. And the visual representation, a lot of work right now, including ours, is using set of marks representation. What that is basically you put bounding box around every clickable element, and you associate ID with that element. Right? So the agent can take a look and say, click on element ID 33, or type something into element ID 17, right? These kinds of things, you can just generate. A lot of websites have that with just a simple Java plugin. So you sort of almost gives you kind of like parsing representation of the visual input, right? Think of it as like a perfect semantic segmentation, right? You have that. There are other ways of doing this. It's something like grounding that people are working at using coordinate sort of approaches. Like you can say like go to like coordinate 5637 and then click on that element, but that's still very much work in progress. And so how does it work? Let's say I give you the goal. I'm trying to find post, navigate to the comment section for it. This is my observation. I have an image and I have some form of accessibility tree, some form of HTML representation. I augment it with set of marks, right? So I associate each ID with a box around it so that the agent sort of has some notion of what I can click on, what actions I can take. And that goes to the multimodal LLM that understands both text and visual representation. And then, it generates typically what we call chain of thought, or it generates an explanation of what it's trying to achieve, right? It says, let's think step by step. The objective is to navigate and find, post and navigate to the comment section for it. From observation, I can see to navigate to this listing, I need to click on the comment link associated with sushi. In summary, the next action I will perform is, and your action is click 34. So that's a discrete action, and then the element ID. Okay. And of course, training these models is difficult. Part of it is that, way to get data like this. It's not like when I'm browsing and explaining everything that I'm doing, right? But unfortunately, you need that kind of data to train these models. So there's a lot of work happening on actually annotating what people are doing, how they're doing, and an explanation of what they're doing. And so your action is actually specific predefined action that you take. Okay. In terms of what the existing models can do, if you only use text-only models, you hit something like 10%, right? These are the best models, including, GPT, Gemini, sort of. If you use text plus captions, because the other thing is that to forget about the multimodal piece, just caption what's happening with images on the web and represent everything as text and do that. Multimodal gives you a better representation, and set of marks gives you a slightly better representation. But that gain here, from here to here, is actually significant. You go from something like 13% to something like 19%. So you do solve a lot more tasks if the agent actually sees the visual representation, right, of the input. And this is where humans are, right? So in terms of what they can do versus what the state-of-the-art models can do today. What's surprising, what we found, and these are students, so they're smart. Obviously, they're CMU master students. These are all grad students who were solving these tasks. So, but we found it surprising that there was a gap to 100%. You go from something like, I think the performance was like 89%. Care to guess where humans would fail? What do you think? some of these tasks, like, hey, find me the printer, send it, find me this, do, solve certain things for me. Yes.
Just like typos and addresses and things like that? Or?
No. Yeah.
I can imagine if tasks are very tedious and require multiple steps, the students at some point give up.
Yes. So what ends up happening is I go to Craigslist and I say, hey, you know what? I want to buy black Toyota, which is at least 3 years old, or less than 3 years old. Find me the cheapest one, and then offer the posting. What happens with students is that they go, they find one Toyota truck, they find another Toyota truck, and they're like, I'm done, right? Find the cheapest one and make a posting. And that's a mistake because there's like 10 other Toyota trucks, and I'm not going to do that. Now, of course, there's an argument for that. Like if we paid them more for finding the right answer, they'll probably solve the task. So we can drive that to 100%, right? The other mistake that would happen a lot of times is that they would actually solve the task, but they would forget to click on like place the order. So they get it, and then they forget to make the last action. And our model basically says, well, you didn't solve the task because you didn't place the order, right? And this is where I think that agents can actually do a much better job than humans. Like the fact that I'm finding some information, I can actually do it way better than humans can, because I can search through the whole thing and find black Toyotas and sort of find the right answer, right? So that's just kind of the argument. But of course, you can kind of like see there is a big gap. Yes.
Other than chain length, what are the other like hard things for the AI?
I'll come back to this. Yes, I'll come back to that. I mean, there is a lot of things that these agents are. So for example, one common thing is that these agents right now don't have memory. And so what ends up happening, they keep bouncing between like, try to do this, try to do this, and then try to do this. And you kind of like get stuck in the loop. I mean, these things you can fix. A lot of it is visual processing. It just doesn't understand what the input is. A lot of time it's failure or stopping early. A lot of times it's like, I'm asking you to buy a blue shirt. It goes, finds the information, ends up on a web page only with black shirts and says, I can't solve it. There's only black shirts and no blue shirts. And so there's this notion of like, okay, stepping back and doing a little bit of exploration could solve the problem, but a lot of these systems don't. So, yeah. And the way we can kind of like think about some of these agentic capabilities is that, we have some observation, we do some parsing of the observation, we have an objective. There is some work on trying to do planning or reasoning. That's important. Sort of generating high-level plans, and then you generate low-level actions, right? And you may refine high-level plans and so forth until you stop. Yes.
So one question to this, you might have said it at the beginning, but this is all within one context window where we have like one LLM and then it just always generates the next answer. This is a multi-agent setup where certain parts are kind of outsourced.
So right now we're always operating with a single agent. It's a single agent. We give it the objective. The agent has to do some kind of planning, or doesn't have to do, but ideally do some kind of planning, some kind of processing of the input. Both of them are very important. And then you have to execute the low-level action, right? And so, for example, planning is actually one interesting problem that we'll see later in the talk on the physical agents. But if I'm trying to sort of shop for something, right, you can imagine there could be high-level plans like navigating, sorting, selecting, and buying that you can transfer across many different domains. And then, here you have one low-level action. Here you have, 2 low-level actions and so forth. And then you have 3 low-level actions. And so there's been some work on sort of planning, somewhat successful and somewhat not. But that's a very interesting area of research. Here's another task, which is kind of, it's a successful execution, which is, I don't like the author of this image. So somebody posted the image from one of the posts in F memes. Can you help me block them, right? And so the agent has to like do multiple steps. It has to search for the F memes. It has to find, it has to navigate, it has to find a particular user. It has to click on a bunch of elements to actually block you, right? So this is, again, this is an example of a successful execution. And you can see it's highly non-trivial thing to do, especially for the agent that haven't been specifically trained or fine-tuned to kind of like deal with Reddit-like examples. right? And so we can think of VisualWebArena as a way, as a step towards building these general purpose agents, of course, but tasks are not very consequential, right? You can argue that they don't represent a lot of economic value. Tasks are simpler right now. These tasks are actually fairly simple tasks, and LLMs do not even perform well on these tasks. And obviously, long term, you can think about automating productive, economically valuable tasks, whatever these tasks might be. And there is a lot of work, at least in CMU, trying to figure out what that could be. So for example, we could simulate many tasks from, there's a database of all jobs performed by the workers in the US, created by US Department of Labor. There is some efforts trying to go through these tasks and see how many of those tasks potentially you can automate. It's an interesting exercise, actually. A lot of these tasks potentially can be automated, but a lot of it also requires breakthroughs in building these agents. And I do think that the multimodal models are very important because a lot of these tasks require some visual grounding. Anything you perform in PowerPoint, Google Sheets, or Excel or Photoshop, to have these general agents, you need to build strong visual language models. And I think there's a lot of work right now happening in an industry, in particular because of the scale, to build something that actually has very good grounding of visual representation, right? Some of the failures of existing models, as I mentioned before, models tend to oscillate between web pages, so get stuck in the loop. So it's like, hey, go to Reddit, do this, and go to Wikipedia, and then from Wikipedia, go back to Reddit, and go back to Wikipedia, right? And like sometimes just get stuck and then dies. You sometimes on the correct path performing task, and then these models go and undo these tasks, and so you have like these weird trajectories. A lot of times the agents tend to stop exploration execution earlier. So a lot of times they generate stop actions, and I'm done, can't solve the task. Obviously, there's a lot of fails in visual processing. Sometimes you click on the wrong thing. You can't identify specific items in complex web pages. Spatial reasoning sometimes is failing. Hey, what are the prices of product in the first row? Like sometimes that part is also missing, right? Yes.
When you mentioned that agents don't have like a long-term memory and they might like bounce back between two, so are you not putting like the history of agent actions into the context for like executing?
Yes, the one way to fix this problem would be to keep putting the entire history of what you've done so far. The problem is that you have to be very careful how you do it, because like both the visual processing becomes tricky and the context becomes large. And as your context grows, the performance of these models actually decreases. So they're not very good at using context efficiently. At least that's what we've seen with existing. It might get better, but so you have to have something smarter to kind of like represent. People have looked at some form of VAEs or ways of constructing and sort of compressed representation of the history. And there have been some papers follow up on this work showing that you can actually have an improvement, but still an open research question. I think there was a question over there.
What do you mean by like they perform worse in the sense that like they get worse at recall, or yeah, sorry, what do you mean?
Performing worse basically means that on VisualWebArena, like give you the task, how many of them you can solve? Right, because for us, it's a very well defined. It's just, did I end up in the correct state or not for the task? I don't really care how you get there, but did you end up in the correct state?
Does it help if you include previous examples of correct solutions in the context? Like
no.
Context,
yes, you can do that. That's right. But you have to be careful how you use the context, right? So right now, for these kinds of experiments, we didn't use the context. So right now, it's mostly like you get a sequence of actions with the chains of thoughts of what you've done, and then you have a visual representation of the current state and the HTML for the current state. And then that gives you information of what your next action should be. Perhaps there are better ways of absolutely doing that. Yes, there was a question here.
So M method you mentioned, so it gives you like clickable items, lots of them. And so each clickable item, how do you give its meaning? Like, do you use a vision transformer again, or how do you do the capture?
Yeah, I mean, right now, a lot of these models, like GPT models or Llama models, they have a visual encoder, right? The visual encoder encodes the entire image, right? And it has to output what element you want to click on, right? So it has to understand the set of marks representation. A lot of these models do understand. I think they were trained at the pre-training and then maybe post-training. They kind of have a mention of what these bounding boxes are and element IDs associated with them. Yes. We're not touching Yeah. Yes.
What do you think is the value of making agents that can replace those jobs besides learning that we can do? Do you see a real economic or like humanitarian value to doing these things?
To what kind of like things?
Go to the previous slide where you said that they're, yeah, like figuring out what kind of jobs they can automate.
This is mostly right now, it's more of an experiment for us to sort of, we have a grant with Open Philanthropy to kind of like see what kind of like simulators we can build and what kind of things we can go beyond just shopping online. Right, so what are some of the tasks that potentially could help people kind of accomplish those tasks faster? And this is a very good way for kind of like see what can and can't be done, potentially. But it's still very early because a lot of the tasks over there actually require you to have a very good communication and very good planning and very good sort of, techniques. So it's very hard at this point to replace humans with these agents. We're not there yet. But for us, it was just an exercise to go through it and see what potentially we can do. Because these tasks right now that we're solving, they're kind of like toyish tasks. Might not be of any sort of consequential value. Yeah, yes.
Do you have any unique or interesting ways of making the WebArena more robust, or basically like maybe have some buffering for slow internet connection, or maybe have some malicious sites just to like bridge the gap with the actual?
So yes, on malicious sites and the safety, I'll come back to this at the end of the talk. So let me maybe just one last question and then I'll dive. Yes.
Any websites, there might be multiple ways task agents always picking up every most sort of trajectory of doing a task, or do you see a lot of variation that, and that leads to accurate outcomes?
Are you saying like how efficient they are in terms of solving versus kind of like doing random stuff and then solving?
They might be right eventually, but if the path going right is always like the most effective.
Yes, I think that's a good question. I think a lot of times you actually put the budget constraint, right, for how long you can kind of like explore. That's number one. And then the second one, typically the agent would generate a stop action. And if it generates the stop action, then that's the when we stop. You have a special token that basically says the agent basically telling you, I'm stopping. And then there is a budget constraint where you say like, I cannot do more than 20 steps. If I'm doing more than 20 steps, I stop. And the reason we do it is because otherwise it becomes too expensive, right? So there is a cost associated with running these agents. Maybe one just last question and then we can.
If we have many paths to solve the task, it can be optimization.
So I'll come back to that. It's a very good question. So what is it that we need to do? Reasoning and planning over long horizons is kind of like very much an open research problem, right? You also want to allow agents to search. So for example, you can think of it as executing, coordinating, and coordinate multiple instances in parallel, and maybe ask for clarification confirmations, right? You also need strong visual language coding models because there's some work that actually uses code to improve some of these agents. And of course, you need some kind of like level of abstractions for HTML screenshot APIs. But let me jump into the second part, right? There's a few questions of what we can do to improve these models. One of the interesting things about these agents, and again, people who worked in this domain is not surprising at all, is that there is exponential error compounding in these agents, right? So if I'm accurate at 90% of taking the right action, if I'm taking 10 actions, which is common, I'm not very good. I need to be able to kind of like be in this regime over here, right? To be able to, be able to solve these tasks. So I actually need to have a policy that takes the right actions with very, very high precision or with very, very high accuracy, right? Otherwise, you have the exponential compounding errors, and so your agents basically will fail. So one of the things is, anyone who worked on Monte Carlo research or sort of like any sort of inference-time optimization algorithms will know that, local decisions lead to global consequences, right? So let's say if I say add coconut milk to my card, then I can click on element ID 31. Okay. I can click on element ID 24, right? And there's a bunch of paths. In fact, there are exponentially many paths, right? And let's say that's the right path. That gives me the right answer. And let's say I have these probabilities associated with my first click, right? With my first action. And obviously, this is the wrong and this is the right, right? So how do I go finding, what the right path should be? Now, what we found is that one way of doing it, naive way of doing it, is sample actions from language model until you hit the stop. Okay, this is your sample. You evaluate the resulting trajectory. You say, did you solve the task or not? And then you didn't, and then you repeat. Okay, straightforward algorithm, right? So you kind of like repeat, and then that didn't work, and then okay, that did work. So that's kind of like sometimes what's called rejection sampling. It's very inefficient, but it turns out actually, we found that this sort of like simple repeated sampling actually helps. So what we call the oracle here basically means if I generate 10 trajectories, right? And if I know if any one of those trajectories gave me the right answer, I consider it to be correct. In practice, I don't know. So I have to have some reward model that tells me like, this is good, this is bad. Because I don't know when I write in the real world, I don't know which one is correct, which one is not. But at least at the training time, we know what's right, what's wrong. It tells us that repeated sampling actually helps. Okay, and the space is exponentially large. Can we guide exploration? And so the idea is very simple. We're going to be learning a value function that we're going to be applying to intermediate nodes, right? Standard idea, and we think of it as like some form of a best first search algorithm, right? So what ingredients you need a baseline agent to propose actions, right? So the baseline agent has to be good enough. You have a way to backtrack the environment. That actually turns out to be engineeringly a little bit tricky to do, but this is what we would call resets, right? Like you're in a particular state, you propose different actions. You can go to these different websites, but you have to have a way to go back to the previous state. Right? And then a value function. We basically have a way of somehow estimating, given the set of previous observations and the series of actions and the current observation, how do we basically estimate how good these states are? So these are standard value function. You can think of a value function as sort of estimating the expected reward or estimating, are you going to be succeeding or not? Think of it as, am I going to succeed or am I not going to succeed if I'm in that particular state, right? And so, for example, we have some ways of estimating. The question is, how do we do the value function estimation? Well, in our case, very naively, we prompt the multimodal LLM, and it acts as a judge or as an evaluator, right? So we give it the full trajectory, the task, the full trajectory, and we ask them all to say, how good you think the current state is, right? It's not perfect, but that's something that's easy to do, at least as a validator. Ideally, you'd want to build your own value function, right? Or your own, what's called, like sometimes people call it like the intermediate reward models. It's essentially telling you how good each state is when you take a particular action. Think of it as a Q function that you're trying to estimate. Yes?
This is something that's just zero shot, not fine-tuned.
This is something that's zero shot, not fine-tuned. Yes, we typically provide like 3 shots. We typically show some examples of how to operate, and that's where we are. So definitely, you can definitely do much, much better. It's a very simple way of just building the value function. So here's what, now one thing I want to mention here is the backtracking, right? And something to think about is that there are certain actions you can't backtrack from. And we'll talk about those. So we have to be very careful. Like if you can't just buy an item and say, you know what, go back to the previous state, right? I bought the wrong item, go back to the previous state. So there's certain things that we have to be careful about. And that's the good thing about simulators. We can do whatever we want, whereas we can't do them in the real world. So here's an example, just to walk you through. Let's say you have a task. Can you add this and the other canned fruit, the same brand, that looks like this, but red instead of brown, the comparison page? So the tasks actually were, we actually designed those tasks. The actually master students were designing those tasks. It's very impressive. So these are human-generated tasks. They're not perfect, but that sort of gives you the idea. And so, you start, you have some estimation of the value, and then like think of it as a Q function. And then if you have different actions, you have value function estimation for those actions. You take the next step, and then you sort of backtrack to the previous one, right? you kind of like keep rolling and then you backtrack to the, so you always, it's kind of like a best first search approach, and then you get to the success, right? So this is something that we can, basically it's a form of, A star search, or best sort of search, with the way of building value functions at every single step. So you have to have an estimation of the, in this case, I guess it's a Q function, right? We have a state range. So we're always trying to understand, you're in particular state and you take particular action, what's the expected sort of reward that we're going to get? What's the expected way of succeeding, okay? And what we found is that we actually have substantial boost in performance. I mean, this is non-trivial from 15% to 90%. It's non-trivial, and for WebArena, for VisualWebArena, the gains are actually quite higher. So this sort of is telling us that these search techniques are actually inference-time search techniques that actually improve these models quite substantially. Of course, the numbers are still quite low, but we actually do see a lot of tasks we couldn't solve before. We can solve by running this essentially a tree search algorithm. Yes?
There are no error bars. Is it bigger?
No, yes. I mean, the real reason why there are no error bars is that compute cost is expensive. So, you spend like a few $1,000s to do these experiments, and then you basically say, right, it's like each error bar is going to cost you a few $1,000s. I mean, that's the main reason. But yeah, I think we've run a few of these experiments. I think the error bars are actually pretty small. Maybe you can think of it as like plus minus a couple of percent. So the gains that we get are significant gains. And we sort of see on subset of the tasks, as we increase the budget, performance improves. It's not kind of like it plateaus. So it basically means there are certain tasks that these models cannot solve, period. Right? Because a lot of times what ends up happening is that the model doesn't understand what it's trying to do. There is no way for you to solve the task, even if you're doing the brute force, because this space is exponential. But we do see, the depth and the breadth, so kind of how far we traverse versus how, the breadth of how many actions we take. The more we spend time, the more we sort of gain the accuracy, right, on a subset of these tasks. So it sort of points out to the problem that maybe search is something that we can actually do. Of course, having a good value function is essential. And then, of course, there is still a lot of room for improving the base agent policy. So obviously, these agents are not good enough. But the kind of value function that we're using, you can kind of like see with, search, and this is the budget. You can think of it as sort of like the budget, and, the numbers keep going up, right? So the more expensive the search is, the better the numbers are. But I think at this point, we're still plateauing. We're not reaching human level performance by far on these models. So it's an interesting kind of environment to study, because it's sort of real environment, these real data, and it actually simulates real, web crawling. There was a question.
Just a clarification question. What did you classify as state? Is it just that page, the link?
So the way that I think about this, think of it as a simulator. The simulator has some state. The state itself is the internal representation of the web page. From that web page, I can generate the vision part. So I'm generating HTML, and I'm generating accessibility tree, and I'm actually generating from the HTML the actual representation of the web page. Right? So when I click on any particular action, my state transfers to the next state, and then from that state, I'm generating HTML, I'm generating accessibility tree, I'm generating the web page. Right? So that's the state. It's just the state of the simulator. So in principle, the state has everything in it. Right? But what you observe, you only observe the web page, the HTML, or accessibility tree. These are some trajectories, right? I recall seeing this exact item on the site, helped me find the most recent post of it. I recall seeing it in the collective for antique section, right? So it's actually through the search, some of these things, well, here's an interesting one. I need something like this for my apartment. Can you add it to my wish list? That would be cool if this worked. You take a picture and then sort of finds it and adds it to the wish list, right? So this is the case where, again, these agents sort of get. Now, search is slow, right? We've implemented backtracking in a relatively naive way, few engineering efforts on that side. As I've mentioned before, dealing with destructive actions on the web is very difficult. Like, you can't order and then unorder. So there's certain things you have to be careful about when you actually deploy this in the real world. Now, the last thing I wanted to kind of mention is that search as a policy improvement function, there's a lot of work now basically using search to coming up with the right trajectory and then using those trajectories to train your model. That's something that people kind of do in academia and in practice. Is a very interesting way to sort of like use the search to find the right trajectory and then use it as a supervised signal for training your model. You want to also improve the value function by fine-tuning instead of prompting. So you want to have a model that actually understands what the value of the state is. And of course, there is, compute trade-off between sort of how much you want to invest into baseline, getting a baseline agent to be good versus doing more search at inference time, right? And of course, what if we don't have a perfect simulator? That's an interesting question, is that can you actually do it on the real web? That's one question that we're thinking about a lot, is how do we actually go on the real web and do something like this to collect the data? Let me also, in the last sort of 5 minutes, talk a little bit about the physical agents. So I've talked a little bit about digital agents, right? These digital agents that can take actions on the web. But we've also been looking at physical agents, agents that can manipulate objects in the real world. And the idea behind these agents are pretty much the same as the digital agents, right? You have some parsing model that kind of like understands what's in the environment. You have a planning module that plans the sequence of actions that you need to do, and then you execute low-level actions. So we've been building what we call plan, sequence, and learn setting, where you have an LLM that gives you a sequence of plans of what you need to execute. There is a parsing module that understands the visual representation, and then there's a low-level action learning module that learns how to interact with the actual objects, right? So for example, the planning module, I give you state termination conditions, I give you task description, I give you what the format of the output should be, and I tell you what my task is, and the model basically defines what my sequences of steps should be, right? Grasp the silver nut, put it in the silver peg, and then grab this, and then put it there, right? So this is something that LLMs are actually pretty decent at, coming up with these plans. And just very quickly, you have the input representation, you have the depth, you do semantic segmentation, and then we use what we call motion planning to actually plan the motion to a particular object. And then what's interesting, we're also learning what we call a local RL policy for interaction, right? Once we're near the object, we can actually learn how to interact with a particular object. So in simulation, kind of like looks like this. And so we sort of like trying to place something, you training with a task reward. It's a single RL policy trained across many, many different environments, many different skills, and it's local instead of global observation. So observations are local so that we can just interact with the object. And in terms of what the full pipeline looks like, we do have a plan. We do pose estimation and then motion planning to plan to a particular object, and then the low-level control via reinforcement learning that learns how to interact locally with the object, and you sort of proceed in that manner, right? So executing a sequence of steps. The devil is in detail, but you can kind of like build these models in simulation, and this is one of the long horizon robotic tasks where you actually try to execute multiple tasks. And then in the last few months, we've been spending quite a bit of time to actually transfer what we learn in the simulation into the real world. Much like what we're trying to do with the web agents, we learn in the simulation and then try to deploy these agents in the real world and see how well they can do. And so for these tasks, it actually, here's the task, put the mouse in a drawer and close it, right? So here's something that was trained in the simulation and then works in the real world, right? So you can put the tape in and then close it, and so the language model creates a plan of what you need to do, and then you're sort of executing these, and it sort of does reasonably well. I mean, you can see the success rate, 60%. You have to have 6 stages, so you have to do multiple stages, and it turns out to be like very difficult to bridge those stages. And here's an example of generalizing to new objects, geometries, categories. It's kind of like trying to interact with different objects and placing them. And again, this is one of these examples where what we call local RL policies, where we learn them in simulation to interact with these objects locally, and then we transfer them to the real world. And it's sort of works in the real world, not perfectly, but kind of works. And then you can sort of manipulate novel objects and then scene receptacles and, you know, and so forth, right? And you can kind of like deal with deformable objects and a bunch of examples of that sort. So it's, you know, the system is actually not too bad. And of course, I guess I typically show these results, but they're probably not very useful. It's just these graphs I typically show that we're the best across, like, you know, you sort of have to do that. You know, we're doing well across these tasks, but nonetheless. The key takeaways is that, you know, one of the things that we're seeing is that connecting these LLMs by generating high-level plans and for low-level control is actually a very interesting idea, right? So the bridging LLMs that give you high-level sort of plans, and then with low-level reinforcement learning is interesting, right? One of the things that's also becoming more and more obvious is this notion of safety and robustness, especially in the age of autonomous systems. Here's an example of adversarial attack on multimodal agents, where, you know, a lot of these agents use what's called captioning system, right? You look at the web page and you try to caption, in addition visual representation, you also try to caption. So if you hijack the captioning system, you can sort of embed these messages. And what the agent ends up doing is that as it navigates through the web, you know, you can modify what you're seeing on the web. So you can modify the input, or you can modify the images in such a way that, you know, the agent will basically say, this is a terrific item, right? And so it leaves comments like, you know, looks great, for example, right? So imagine the system that's trying to buy a polo shirt. It's kind of like tries to navigate, goes through like, I don't know, some dishes, right? Says, oh, I'm in the wrong way. I should backtrack and look somewhere else. But I'm going to leave a comment saying this is a terrific item, right? And so that's something that you can essentially hijack these agents. There's a lot of work that people are trying to see, like, okay, what can we do to make sure that the agents don't do that, right? Because I can actually modify my website in such a way that these agents will leave star ratings every time they visit my webpage, right? And then also, some of these models are not reliable enough. There was a setting that Claude Anthropic released, right? Where they kind of like take control of your computer and then do something, and then basically, you know, reincarnate. In some cases, Claude accidentally clicked to stop running long string recording, causing all footage to be lost. Another Claude suddenly took the break from our coding demo and began pursue photos of the Yellowstone National Park, right? And the reason why it does this is that it's trying to accomplish the task, and then, you know, you have the web page, you have all the clickable items, and because the policy like chooses a wrong action, if it chooses the wrong action, it takes the wrong action, and once you condition on this wrong action, it starts doing something else, right? It's hard for it to recover. So these are kind of like toyish examples, but also very interesting ones to consider. So on that note, thank you very much, and this work was done by a lot of amazing students at CMU. So thank you. Yes, there's a question in the back, and then.
This is very discrete, right? So you take one, like a few incorrect actions, and then it just goes off, right?
That's right. Or at least for this case, I think it was basically just took the wrong action. Once you take the wrong action, the policy has to produce something else, and it just basically gets refused.
Okay.
There was another question. Yes.
Talked about research performance, a couple percent, 7%, something like that. How many things do you think you have to add, and what kinds of things do you have to add?
So how do you go from like 30% to like 50% or 60% or 70%? I don't know. I don't know how to get there, because a lot of times, basically what it means is that existing models, like these LLMs as policies, are not very good for some of these tasks. The question is, do we just scale them up? Do we just ask millions of people to do these tasks, and we record what they do, and we just train these models enough? Is it going to be an online RL type of a system where the agents will try to accomplish these tasks, fail, we correct them? Potentially, I think there is a lot of applications of online RL for these types of tasks. The only question is how good your simulators are and whether you can go on the real web. And going in the real web is also challenging because you can't go, I was just talking to Sham, you can't go to united.com and like run exploration for booking flights, right? It's like, well, I booked the flight. No, I don't know, book again, no, I'll book again. And then like United's gonna look and say, wow, there's so much demand from flights from Boston to Pittsburgh. I should like crank up my prices, right? It's no longer $300, it's like $3,000. It's like thousands of people trying to do that, right? So you can sort of do these things or they'll just block you, right? That's probably what they're gonna do. But this is sort of, the question is, how do you do it in online fashion? Do you do it in the real world? Do you do it in the simulator? Simulators are very limited. Can you do it in the real world is an interesting question. I don't think human annotations is the answer because it's very expensive and it's a very laborious process, right? So how do you design online algorithms that can do it in a safe way is an interesting problem, right? And not just for the web navigation, for coding. There's a lot of work on coding agents. I want my agents to code and fix my bugs. That has a lot of economic value, right? But if I'm giving permission to my agents to modify my code, safety becomes a big part of it, right? Because the agent can just erase your code base accidentally, right? Can't do that. Yes.
Yes, kind of two questions. The first, just clarifying, what's the representation you're using here? So like when you're doing the multimodal representation, how are you getting this? You're just taking some internal representation from some language model and then...
Yes, exactly. So the way that right now, there's two ways, right? One way is it's an interface to, let's say, GPT-4.
Yeah.
Right? Then I don't have access to the representation. I can just basically say, here's what I can give it, and I'm telling you what the output should be and see, does it give me the right output or not? With Llama-style models that are open source, the representation itself would be the multimodal representation of the top-level features that you're getting before you take the action. And you kind of like get that representation, and that representation contains both visual and the text. So it's like a vector of 4,000 dimensions.
Are you using the representation versus like trying some chain of thought type of thing? Can you ask it like, here are the options, what should I do? Because like a lot of these planning things, like it seems entirely plausible, the language model can plan. But you didn't.
That's true. We haven't done this. So there might be a way to kind of like, when you do the planning things, you can kind of like do like self-correction, or if you like a particular page, you can kind of like ask the language model to say, okay, you've done this so far, like, is this good, is this bad? The only way that we've done it so far is we've done it through kind of like getting a value function, right? Where we basically, at a particular state, we can take the full trajectory with chains of thoughts, and then we can ask GPT-4o Mini or Llama and say, how good my trajectory is if I'm trying to solve this task. A lot of times these models are not bad because you end up in some weird state that, like, if I'm trying to buy polo shirts and I'm ending up in a state that has nothing to do with shirts, the model is pretty decent to say, okay, your value here is close to 0. And what actually helps is that instead of prompting it once, we're actually prompting it 10 times and get some variance estimate of how good it is and take the average. That actually helps.
Part of this is like a question of like how much do we really need the RL here versus just like better like multimodal learning with language and text? Because then, you know, if it was trained on what happens when it clicks some things, you know, stopping these tricks and like mid-training, if you train in some multimodal way where it clicks this, it shows what's happened, then, you know, can chain of thought just do all of this, or give a sense?
It's not clear to me. That's a very good question. How much of it is just a multimodal learning? Because if you have a perfectly predict what the next action should be, you can kind of like solve the task. One difference, what I see is that these kinds of tasks require you to predict the full trajectory rather than just like a lot of multimodal. It's like, hey, here's the image, here's the thing. Can you like tell me what the class or what this is, or like, you know, just one step? This is the multi-step. The other thing there are multiple ways of getting to the state. And so once you start having like many different trajectories to get to the same state, that becomes a little bit more interesting, right? And so I don't know. I think that right now, you know, the question is like, if we just keep collecting the data, how far you can get there. But I suspect there's going to be an interesting work that needs to be done on some kind of like an online perhaps version of RL, like either having a good value function or some kind of system where you go beyond just supervised fine-tuning. But that's yet to be determined. Shom, to your point, I don't know, because I was surprised, that maybe with enough data it will work. It's just the problem is that getting the data is very, very difficult. So you have a way of getting synthetic data. I think that can go pretty far.
What is your reward? Maybe I missed this, but was this like only the distal reward, or do you have like proximal?
We don't have any proximal rewards at this point. We only have the final reward. Because the only way that, we try to basically get some kind of like intermediate rewards, but the only way for us, for now, at least, to evaluate how good the models are is that I give you the task, and I know there is a single state. That's the correct state, right? I know there is only single one correct state for this task. And so whatever path you took, if you end up on the state, we can tell you that, yes. So it's like verifiable kind of, right? And it was designed this way, which might not be true for, the actual task, right? Because
it seems that there are like some of the tasks seem more deterministic, and others like seem to have like an intelligence layer to that. For example, find this T-shirt that has this sort of thing. Just comes up with a sweater that has that. So it's kind of like, okay, so maybe there can be partial solution there, but then if you're just filling out a form with the address and all of that, then that feels like very deterministic. So do you distinguish between these, or?
We don't. Unfortunately, we haven't distinguished between this, like how much you need reasoning versus how much is like visual understanding. We've tried doing this a little bit, asking people, like when they were solving the task, how much of it is reasoning you have to do, how much of it is sort of just sort of visual understanding and just executing. What we do find is that like the longer it takes, the more steps you have to make, the higher the chance that the models fail, even the best models. Even if it's just deterministic form filling, they will mess up somewhere.
It's not like that. That is definitely how these interfaces were designed, because it's called Hick's law, and it is a law on making the interface usable for people, which is essentially breaking the task down and only like kind of step-by-step completing forms, because that's the easiest way for people to complete forms.
Yes, but the way that we're doing form completion is that, you show you the form, you have bounding boxes, elements, and you can choose in any order, as long as you say in element 17, you have to type this, in element 21, you have to type this, in element 37, you have to type this. It doesn't necessarily mean we have to go in the same order. We just have to kind of, but at the end of the day, once you end up in a particular state, the address has to be matching exactly. If it's not, we basically say you didn't do the task, because if you messed up the address, we don't count it as a success, right? So yeah, yes.
Could you give a guess about how clouds train there? Because it seems like it's very different from your method.
I think they're doing something similar. They're building multimodal models, and then they're basically perhaps collecting, human trajectories and how people would solve the task, and then try to imitate that. Basically, what works right now is behavior cloning, which is, you get a bunch of grad students, they solve the task, they annotate how they solve the task, you do supervised fine-tuning on that, and that gets you not far, but it gets you somewhere. That's my sort of thinking is.
Sure. Just how balanced was the performance across the different website vendors? Like I can imagine it'd be less interesting if it's super good at Amazon, but bombs everything else.
I think the performance across all kind of like websites were similar, because some tasks are easy, some tasks are hard. And so I don't think we basically saw like on this task, it's like way better than like on this website, it's way better than on this other one. It was kind of like a little bit balanced. It's not a lot of tasks, like 900, I think, in 30 tasks that we came up with, and sort of uniformly.
Congrats again.
Yeah.